my voice. هل عندك سؤال؟ In the previous session we see Ree's lemma for each Hilbert space H. If we fix an element such as y and define phi by the index y by this function rules, phi y of x equal to the inner product of x and y, we see that this is a bounded linear functional, so that phi y is an element of the dual of H. And moreover, the operator norm of this functional equal to the norm of y in H, and conversely, if phi belong to the dual of H, there exists a unique element y such that phi be equal to phi y, so that we have a one-to-one corresponding between element of H and functional on H It must be noted that the mapping y to phi y is not quite an isomorphism of Banach spaces. It is not linear map, because we know that phi of alpha y equal to the conjugate of alpha multiplied by phi y, because we found a function from H to the dual of H. Okay, we denoted this by for any y in S, we define phi y by this. Phi y in the dual of H, because this is linear and bounded. Okay, and C is full. So if we, let me add another page. Another page. Let me define, for example, psi, okay, from H to the dual of H by this function rules, phi of y equal to phi y. Okay, then this is not a linear function, because psi of alpha y for any alpha in complex number psi of alpha y equal to phi of alpha y. Okay, and we know that phi of alpha y of x equal to, by this function rule, okay, by this function rule, x and alpha y. And this is equal to the conjugate of alpha multiplied by this inner product. What is equal to this inner product? Equal to phi y of x. So that by this observation okay, with this observation, if we denoted this by a star, this equal to alpha, the conjugate of alpha multiplied by phi y of x, and since this holds for any alpha, for any x, we see that this function equal to alpha bar phi of y, and this is equal to alpha bar psi of y by this function rule. So the psi of alpha y is not equal alpha psi of y, and so psi is not, so psi is not linear. Okay, for this reason, in this book it is only conjugate linear, not linear. The dual space H a star is actually a Hilbert space if we define phi y and phi z equal to the inner product of z and y. We must replace the role of y and z for solving this problem. Okay, so this is the inner product in H star, because by the theorem or Ries's lemma, we see that we have a corresponding, a one-to-one corresponding between H and H star, or we can say by Ries's lemma. Let me write by, note that by Ries's lemma, psi is onto, so the psi of H equal to the dual of H, because psi is the function from H to the dual of H, or equivalently we have this equality. Psi of H is equal to all phi y such that y belong to H. This equal to the dual of H. Okay, so that for define an inner product on element in H star, we can define an inner product on phi y. Okay, because element of H star is in one-to-one corresponding by this functional, okay, and this function is onto or surjective, okay, and by the Reed lemma this function, and by this function the above definition define an inner product on H star, and we have this equality, and we have this exercises. This exercise is very important, and also the proof of this is easy. Where is the completeness of H used in the proof of the Reed lemma? More precisely, what can you say about X star if you only know that X is an inner product, not Hilbert space? Maybe this inner product is not complete, okay? And 2, if T belongs to B of H and K, where H and K are Hilbert spaces, prove that the norm of T equal to the supremum of to the value of inner product of T x and y for all x in H and y in K with these properties, okay? This exercise is very important, very important. So please exercise as an homework, okay? Please solve this exercise. Thank you. And we have a definition of bounded sesquilinear form. This definition is very important, and this is an important operator. A mapping B, for example, from H times K to C is called a bounded sesquilinear form if we have this equality. Please note that H and K are Hilbert spaces, okay? So the domain of this product B of any ordered pair such as this summation and this summation, such that alpha I and beta j are complex numbers and xi are elements in H and yj's are element in K. B of this ordered pair is equal to this summation, so that this function must be linear in the first variable and conjugate linear in the second variable, okay? A mapping B from H times K to C is called bounded sesquilinear form if we have this equality and the norm of B equal to this supremum, the absolute value of B of x and y, such that the norm of x and the norm of y be less than or equal 1, be finite, so that B is called bounded sesquilinear form if B is sesquilinear form and B be bounded by these two functions, by these two definitions, okay? The following is easy consequence of Reed lemma. Proposition B from H times K to C is a bounded sexual linear form if and only if there exists a unique bounded operator T such that B of X and Y equal to the inner product of T of X and Y. It is very nice that if we consider any bounded linear function, let me write this for you. If T for example from H to K is a bounded linear function and define S from H times, sorry, this is K, okay, this is another Hilbert S-space such as K. Now we define S from H times K to C. By the following function rules, for any X and Y in H times K, we define S of XY equal to the inner product of T of X and Y. Please note that T of X is an element of K and Y is an element of K. This inner product is inner product in K, okay? Is an inner product of K. Then trivially S is a squilinear function and bounded function. This is an easy exercise, okay? You can check, for example, if we construct S of this sigma alpha I xi from 1 to n and beta j y j from 1 to m, for example, this order pair, okay, equal to T of this summation and this summation. And since t is a linear function, this is equal to this summation alpha I t of xi, I from 1 up to the n, and we have this as second variable. Okay, and since this is inner product in the Hilbert space K, is equal to this summation alpha I beta j bar t of xi and yj, I from 1 to n and j from 1 to m. And we know that this is s of xi and yi, so that this is equal to I from 1 to n and sigma j from 1 to n alpha I beta j s of xi and yj. Okay, so that we have this equalities, and this is a set collinear, and this is bounded, because if we consider this supremum, also we have the norm of this S equal to the supremum of this set absolute value the absolute value, the supremum of absolute value b of x and y, so that we have supremum of s of, in this case we define s such that the norm of x is less than equal 1 and the norm of y is less than equal 1, but this is equal to the supremum of tx and y, this inner product, such that this norm is less than or equal 1 and this norm is less than or equal 1. And this is by the Cauchy-Schwarz inequality is less than this, then this norm and multiplied by this norm, such that this norm is less than or equal 1 and the norm of y is less than equal 1, so that we can consider this equal to 1 and this supremum equal to the norm of t. This shows that this norm is bounded, so that this function s is a bounded square linear function, so that for any bounded function from h to k we can construct a square linear bounded function from h times k to c. In this theorem, we see that for any t, conversely, for any sesquilinear and bounded function from h times k to c, we have n t as a bounded function from h to k such that we define as our example. So any bounded sesquilinear function constructed by one bounded function from h to k, and the norm of t equal to the norm of b, and every sesquilinear form defined on h times h satisfies the polarization identity. This is polarization identity, okay? And this is I or non-real unit, okay? Is equal to I. It is a consequence of the open mapping theorem that the following conditions on T are equivalent. There exists an S in B of K and H such that ST equal to identity and TS equal to, this is composition, okay, of function. If T belongs to B of H and K, please note that. And S belong to B of K and H, then T is a function from H to K and S is a function from K to H, so that we can consider this composition, okay? ST is meaning SOT. SOT. Now, if there exists an S such that ST equal to identity and TS equal to identity, this identity of K and this is identity of H. So this function is from H to H, okay? But this function is a function from K to K. This equal to T is a theoretic bijection, but one to one and on to. Dear students, please, okay? If have another operator such as S by these properties, we say that T is invertible and write S equal to the inverse of T. It is the fact that the collection GL of H and K of such invertible operator. GL of H and K is the set of all bounded and linear and invertible function from H to K is open in the norm topology of this space, and that the mapping T map to the inverse of T is norm continuous map of GL, H and K on the, we see this theorem, okay, we see this theorem in the previous sessions, not for Hilbert spaces. In Banach spaces we see this, okay. And recall that the spectrum of a T in BH is defined to be sigma T, the set of all complex numbers such as lambda, such that T minus lambda is not invertible, okay. It follows from the previous paragraph that sigma T is a closed set. It is also true that sigma T is a non-empty compact set for any T in B of H. An elementary fact about spectra that will be needed later is a special case of a more general spectral mapping theorem. Spectral mapping theorem. And this is an important theorem. This proposition is called a spectral mapping theorem. If P belongs to C of T, C of T is the set of all polynomial with complex coefficients and variable T. And if T belongs to B of H, then sigma of P of T equal to P of sigma of T. So we can change the role of sigma and P in B of H. So please note that CT is the set of all polynomials with complex coefficient, okay. Or we can say that okay. Ct equal to the set of function by this form. For example, alpha I, T I from 1 to n, such that n belong to n union by 0, sorry, so we can write from 0 and alpha I be complex numbers, so that this is a polynomial, okay, with the variable t. Now in the spectral mapping theorem, we say that for any p, this p, so that it is a polynomial, and for any t we have this equality. H is a Hilbert space. P belong to C of t, so this is a polynomial, and T belong to B of H. T belong to B of H, then we have this equality sigma of P of T, P of T equal to P of sigma of T. And this is its nice proof. Fix a lambda in C, complex number. If P is a constant, the proposition is obvious, okay? If P be constant, because constants are polynomials. If we consider n equal to 0, this is equal to 1, and this is an scalar. So if P be constant polynomial, if P is a constant polynomial alpha, for example, then we see that, so that this is T, capital T, because this is a linear function. This is T, okay? Okay. This is T. Then sigma of pt equal to sigma of alpha, and this t equal to alpha, so that this is equal to p of, because p is fixed, any element map to sigma of alpha, okay, is equal to p of, okay. So if p is constant, we have this equality. So we assume p is a polynomial with degree great or equal 1, so that this polynomial is not constant. Then the algebraic closeness of C permits a factorization of the form pt minus lambda equal to this. Please note that in this case p is not a constant, then n must be greater or equal 1. Because p is a polynomial, so that p have a form by this, okay, alpha I t I from 0 to n. This n must be greater or equal 1. In this case, we know that p minus lambda, okay, p minus lambda for any complex number lambda, p minus lambda is a polynomial in C, okay. So by algebraic completeness of complex numbers, this polynomial have a factorization such as Kitab write this, because this polynomial must be separate to polynomial with degree 1. Every polynomial with complex coefficient have roots. Okay, have roots. This is completeness or algebraic completeness in complex numbers. Such as this, t minus mu I, pt minus lambda equal to this multiplication and coefficient t minus mu 1 multiplied by t minus mu n. Let me emphasize that every elements such as Q in CT have roots in complex numbers. This is the root of this polynomial. This is the polynomial, okay? Such as Q. You know that if we have P be a polynomial, okay? And P of mu equal to 0, then P equal to T minus mu multiplied by Q, such that Q is a polynomial. Of course, if the degree of it is equal to n, the degree of this must be equal to n minus 1. So we can write, if P belongs to this with degree n, with degree n, with this Q is with degree n minus 1, and by continuing this process, this Q can be write as another and another roots. Finally, we can write, if this call it P1, this is mu1, this is T1 mu1. Then we can find the root for Q, and finally this P can be written by this form: T minus mu1, T minus mu2, and T minus mu n. Okay, at most n root we have in this factorization. So this polynomial can be written such as this production. Okay, clearly then pt minus lambda equal to this. We must put instead of t this function, okay, where the order of the product is immaterial as the factors commute pairs wise. We need the fairly easy fact that if t1 and tn are n pairwise commuting operator, then the product t1 tn is invertible if and only if each ti is invertible. And this is very very easy. This is a very easy practice. Note that if T1 and Tn in BH are functions such that are pairs was commute, okay, pair was commute or pair was commuting operator. Our problem is this, the invertibility of this function. Then T1, T2 and Tn are invertible if and only if this product is invertible. The proof of this very easy because this is trivial. This is trivial because if T1 up to Tn are invertible, then we see that this product is invertible because the multiplication of this and this function, okay, equal to identity because the composition of operator is associative, so that this is identity and another finally T1 or T1 inverse equal to identity, so that we have this inverse, or we can write the inverse of this element equal to, so this is n. This is n. Is this function Tn inverse or T1 minus? And conversely, Conversely, let T1, T2, Tn be invertible. Okay? Then there exists a function s in B of h such that T1, T2, Tn os equal to identity. Okay, you see that? This function multiplied by this function equal to identity. And conversely, and also we see that T2, T3, Tn. Okay? Of S multiplied by T1 equal to identity. And also for T2 we see that T2, T1, T3, Tns equal to, because all of these are commuting, equal to T1, T2, T3, Tns, and we know that this is equal to identity. And other function is invertible. Okay, other function is invertible, T1, T2 and other, so that if this an invertible function, all of this must be invertible, and this is an easy exercise. Okay, we need the fairly easy fact that if T1 up to the Tn are n pairs was commuting operator, then their product is invertible. It is invertible if and only if all of this is invertible. Hence, conclude that lambda is not in the sigma of P of T if and only if all of this mu I is not, because lambda is not in sigma of P of T, meaning that P of T minus lambda is invertible. Okay, lambda is not in this. Let me write for you. Lambda is not in sigma of P of t. So lambda is not in sigma of pt if and only if pt minus lambda is invertible. This holds if and only if all of this, because we have this equality, this is invertible if and only if all of this be invertible. This is our ti, for example, and this is t. Okay, all of this be invertible for any I in 1 to n, for any I in y to n, t minus pi or t minus mu I is invertible. Okay, and this holds in if and only if for any I in 1 and n, mu I not belong in the sigma of t. Okay, equivalently lambda is an element of sigma of p of t if and only if the negation of this is the negation of this. There exists an I0, for example, in 1 to n such that mu I belong to sigma of t. Belong. Equivalently, lambda is an element of this if and only if there exists some I or I0 such that mu I belong to this. This is equivalent to saying that lambda belong to P of t. Lambda belong to P of sigma of t, because it is very important, because by this equality P of mu I minus lambda equal to 0. Please pay attention. Pt minus lambda is very nice. You simplify that. Simplifies that lambda belongs to sigma t. Lambda belong to P of sigma t, because for this we know that Pt minus lambda equal to this alpha t minus mu1, and this is y0. Okay, I0, I write I0. Okay, multiplied by t minus mu2 multiplied by t minus mu n. So P of mu I0 minus lambda equal to 0, because one of this is mu I0. Okay, we can write more complicated, for example this, and finally t minus mu n. Okay, if we put mu0 instead of t, this item equal to 0, so that all of this equal to 0. This shows that P of mu I0 equal to lambda, and this shows that lambda or P mu I0 must be belonging to P of sigma t, because we reach to this test, this is an element of sigma of t, so that P of mu I0 belong to P of this. This is P of mu I0. And this is if and only if, so that we can see the converse of this process, so that lambda is an element of this if and only if lambda is element of this. And this is the proof of this important theorem. Okay, dear students, okay, we continue in the next session. Mr. Ali Al-Shahmani, I turn off your microphone. Mr. Shahmani, do you have my voice?
Hello, sir. Welcome, sir.
Hello, how are you?
Hello. I'm fine. How are you too?
Thank you. Please talk.
Doctor, yes. So first, can you present the homework again in the lecture?
Please repeat, Ali. Your voice is very weak, Mr. Shahmani.
So, have my voice?
Yes, please.
I have two topics, please. Firstly, can you present the homework again in the lecture?
I sent to you. You want I sent to you all homeworks?
Okay, no problem. Secondly,
Okay, I see, and I tried found all homework and recall this in WhatsApp group. Okay.
Doctor, secondly, please, are you at the university this day?
Yes, I am.
Yes, we want to meet with you and a group of students to discuss some important topics.
This day?
No, this day. Tomorrow, after tomorrow, no problem.
Okay, tomorrow maybe in how in 11, okay?
And 11, no problem. Thank you, doctor.
Thank you very much. See you later.
Thank you, doctor.
Goodbye. Goodbye for now.